Hello everyone, welcome to another physical sciences lesson. We're going to be exploring and revising the topic of electrodynamics. Let's go and have a look at our question for today. So here's a key question I want you to think about. How many different principles are used in electric machines? Now we know how important electric machines are to us, but what is the physics behind them? And what principles do you need to learn? Because remember, you can be asked to state principles, and you've got those definitions in your textbook or in the exam guidelines. You need to learn them. Make sure you've got them, because that's easy marks to get on this section. So let's have a look at our concept map. When we talk about electric machines and electrodynamics, we're talking about the electric motor, and we're talking about the generator. Now, here we need to be very specific. We have looked so far at the direct current electric motor. And that electric motor that uses DC has a split ring commutator. Very important that you use not just the word split ring, you must use the word commutator when you're describing the direct current electric motor. When we've spoken about the generator, we've spoken about the AC or alternating current generator, and that has slip rings in it. So please be very careful that you understand the components of these electric machines. But my question to you wasn't about their structure. We're going to compare them a little later. But for the moment, what I want us to think about is what makes them work. And here on the concept map, we recognize there's a relationship between the force, the coil, and the current in the coil, and the magnet. This relationship is the important thing that makes it work. So let's revise. The principles that we're looking at and the terminology that we need to think about is electromagnetism and electromagnetic induction. So can you remember what these principles and observations that we see actually all mean? Well, let's get into it. The first thing that I need to remind you about is the idea in electromagnetism that if we have a current that moves through a straight conductor or a loop or a coil, well, what will it do? It will produce a magnetic field. And that's the principle of electromagnetism. If you want to have a closer look at it, remember that in electromagnetism, it depends on a moving charge, which is a current. What's changing? The charge is changing, the position of the charge, and that's going to cause us to have an induced electric field, either around a straight conductor or in a coil. We'll get a magnetic field being produced. How do we use that? Well, we use that in an electromagnet. Now, you've seen these in many places. On a switch on a door, in an alarm switch, they have electromagnets. You might have even made one yourself, wrap some wire around a nail and connect it to a battery, and it becomes becomes magnetic. They use it for sorting metals, all sorts of applications to it. Remember that we can represent the coil in this way, where we said that when we see the sign for the cross, that means that the current is going in. So current is in at that point, and over here, the current is coming out. The dot is telling us the current is coming out. So the cross tells us the current is going in, and then if you want to look at this coil, we use different hand rules to show the magnetic field. So for a coil, we'd recognize we use the right hand solenoid rule. The fingers all point in the direction of the current, and the thumb points to the North Pole. So look here. The current is coming out of the bottom, and it's going in at the top. So when we curl our fingers this way, the North Pole will be over here, where the thumb is pointing to. That principle of electromagnetism is in fact very useful. And it's even used in an electric motor. We have shown diagrams. We have a permanent magnet creating the magnetic field. But in reality, in many motors, they actually use an electromagnet to create the magnetic field. So that's just a little bit of interesting side comments there. If we were to look at the coil at another position, and we've got another principle that's coming up here, is we'd recognize that the field lines are showing lots of magnetic field lines coming out of this coil. This is a coil, we're looking at the end of it. On this side, the field lines are going in. Remember, when field lines are close together, that means we've got a strong magnetic field. And in fact, we can compare that to, on the outside here, these magnetic field lines are far away. And we use an idea called magnetic flux, which is very important for us to understand. Magnetic flux is given the symbol phi, and it's really about the magnetic field. So this is the field, the B for the field, and this is the area that is perpendicular to it that cuts through it, and it must be the perpendicular area, and we correct when the area isn't at 90 degrees. We correct for that by using the angle. So the angle is taken at 90, and if the area is not at 90, we've got to say what component would be at 90. So over here, the field lines are coming out of the board. The area we're talking about is at 90. So this would be the area here, because the field lines are cutting them at 90 degrees. And that's the important principle of magnetic flux. Please make sure you understand magnetic flux. And of course, what we do with that is we're going to apply it when we look at another idea of electromagnetism. The thing that we're going to look at here is the principle of electromagnetic induction. So another application of electromagnetism is the electric motor. Now, you'll be aware that the electric motor is very important to us because it's the electric machine that we're focusing on. So let's just make sure that we understand what happens in an electric motor. The motor effect is the thing that we're looking at here. And it deals with magnetic flux as well, because we're looking at field lines in an area. And here we've got lots of field lines and they're interacting with each other. Remember, in this diagram, we will have the field lines from the permanent magnet, which is from north to south. And over here, we've got the field lines that are created from the conductor, from the current in the conductor. And if we use our right-hand rule now, the current is coming out of the board, and you can see, I'll use a different color to represent those field lines. We use the right-hand rule to show the curl of those is in the anti-clockwise direction. So around here, we've got field lines that are going to be in that direction. Now, they can't overlap. That's not allowed. So what I've drawn is I've just drawn the two pictures and I kind of put them on top of each other, but not really allowed. So I'm going to just clear that to show you what the pattern will be, because the field lines over here deflect or move the other field lines out of the way. So instead of the field lines being two of those, what happens is these ones bend. And they bend like that until they look like that. Now, in nature, we don't like bent field lines. We don't like crinkles. We like them to be straight and nice and not stressed. The stress, if this conductor can move, is going to cause that conductor to experience a force. And so it's going to be pushed out. And that's the motor effect. And if you remember, we used the left-hand rule to describe the motor effect. We said, let's take the field, first finger for the field, Then we took the second finger for the current coming out, and we said the force is the thumb. That's going to push it out like that. If you don't like the left-hand rule, you can use the slap rule, where we're looking for the force as the unknown. So we're going to say right hand shows the field, fingers pointing down, the current is coming out, and the slap is in that direction. A little bit awkward, but you can get the point. If you find you have to do all sorts of contortions in an exam to try and get it right, just turn your page, stand on the other side, move around, and you'll find that there's an easier position. So we've covered the motor now. What's the other principle we need to think about? Well, the other principle is electromagnetic induction. And electromagnetic induction is what gives us the generator. Because here we look at a changing field that's going to produce an electric current. It's going to make an electric current. And that's what we are interested in. Do you remember what principle or what law that's related to? Well, of course it is. It is related to moving a magnet into a coil. Let's just illustrate, make sure we've got that. Moving a magnet into a coil. When we move the magnet into a coil or a coil into a magnet, they need to have relative motion. Then we're going to get a changing magnetic flux. And the changing magnetic flux was described by Michael Faraday as being the thing that produces a induced EMF. So in fact, what we're saying is the rate of change of magnetic flux is directly proportional to the induced EMF. How do we use this? Well, we use it in the generator. We turn a coil in a magnetic field, and we're going to produce electrical energy. Guys, I think that covers the important principles that we're dealing with in electrodynamics. Let's take a short break, and then we're going to compare how these two different types of machines operate, the motor and the generator. We'll see you straight after this. Welcome back from that little break. Now we're going to do something really interesting, because I like to be able to compare things when I'm revising. So you might be tempted to just learn all the facts about the motor, then learn all the facts about the generator, but you're just learning those two things apart. Why don't you put them together and compare them? And that makes sure that you really understand, that you're not confused about the similarities and the differences between these. So we recognize that in electrodynamics, we're dealing with the electric motor and the generator. They're both electrical machines. They both involve the principle of dealing with electrical energy and mechanical energy. But they're different, and that's the first difference that I want to look at. The comparison between what energy is being transformed or transferred between the two. Can you think about it for a minute? Let's have a look. So if we look about energy conversion, we recognize we can have electrical energy that becomes mechanical energy. Where does that happen? In which type of machine? Remember, electrical energy, where does it come from? From a stored source of energy. So that would be like from a battery or a power supply, and that's going to cause mechanical energy, turning. So hopefully you can see that in this relationship, this would happen in a motor. But what about the converse or the reverse conversion? If we started with mechanical energy and we ended with electrical energy, so we're making electricity, we're making energy, electrical energy. What process is that going to, what machine is going to do that? Well, it is going to happen because of electromagnetic induction, and the reason that we're going to get that is because we're using a generator. Okay, so there's our first comparison. And guys, this is often a question. Even in multiple choice, you can get these energy conversions coming up. And you need to make sure that you've got them very clearly in your head. What does the motor do? What does the generator do? Very cool. Let's move on. So what are the common components that we find in these two electrical machines? A motor and a generator. Well, it goes back to those principles. We've got the force, we've got the coil or the current, and we've got the field. So we remember FBI, force, magnetic field, current. So the first thing we're dealing with is the field. The second thing we're going to deal with is the current. And we recognize, so this is the field, and we call that B, and the current is I, and then we also recognize there's some sort of force, which I haven't put as a common thing, but there I suppose we can just add it in there. We recognize as well, apart from this collection of magnet and armature, coil put in between the magnets, we also have an external circuit. And the external circuit is either going to supply energy or it's going to use. And that would be the difference between the two. So in the motor, we're going to have the energy being given in, whereas the generator, we're going to have the energy given out. So making this idea of comparisons is quite important and quite useful for us. So the next thing is just to take a look at the picture. And I thought it would be useful to compare them side by side. As you look at the diagram, can you identify which is which? Let's have a look. So what do we notice about these? Here we go. Here's the magnet. We recognize there's the magnet. So that means there's a magnetic field. We recognize there's the coil, and there's the coil. We recognize that there's the external circuit, there's the external. So that's outside. This is external. What do we see happening here? Well, over here is the input, if you like. And the input is going to be the turning of the axle, turning of the coil. So we recognize that that must be the generator, which means that this has got the external battery, so this must be the motor. Okay, so when we compare them like this, we can see that there's some interesting things that we can observe and we can look at, and we can deduce. Guys, what's the thing that stands out, that makes the difference between these, that is very clear in these two diagrams? Well, it's the thing that goes between the coil and the external circuit. So I want to highlight it. It's these two components that we need to be very careful about. There are two different components here, and we have to be able to name them and recognize what they do. So let's be clear. This one that's associated with this motor that is providing direct current, okay, from the battery, this is called the split ring. You can't just leave it a split ring. You've got to say commutator. The word commutator is essential. In this scenario, this isn't just a generator, but it's providing alternating current. So we are dealing here with a comparison between direct current and alternating current. And over here, for this machine, we have not a split ring commutator, singular ring, one ring. Here we've got two rings, and we call them slip with a P rings. With an S, there are two of them. So split rings and slip. So split ring commutator and slip rings too. Please make sure you get those together. But there's an association here that I don't want you to have. I want you to be very clear. You've been associating the split ring commutator with a motor. But the actual association you need to have is the split ring always goes with direct current. What do I mean by that? It means that you can take this thing, which is a very common motor, and instead of having a battery there, you can turn the handle with this and you would make a DC generator. Notice how that's worked. The split ring would become a DC generator. It's no longer a DC motor because you're turning the commutator in. Whereas this one, we've dealt with turning the armature in the magnetic field, and we've said it's an AC generator. But if you have slip rings and you put some AC current into that slip ring connection in the external circuit, you can get an AC motor. The thing that's common is the idea that the slip ring goes with AC, the split ring goes with DC. Please make that connection. If you look at the concept map, that's exactly how we've done it. I want you to make sure that you understand as well that you can not only get a picture like the one we've shown you previously, but you can get one that's drawn in a different position. Notice here we have the split ring, and over here we have the slip rings. So in this case, we're using this as a as a generator, because we are producing, this is a generator because we're producing a load. The external circuit is going to give you the idea. And in this case, we've got the split ring and we're getting a load, so this is DC. So this is a DC generator, just to illustrate it, and this is an AC generator. Please make sure that you follow that very carefully, that you can always see which is which. Right, let's move on. The different components, I've emphasized them, are those, and I want to just make sure that we've got a closer look at them. There's the split ring. Remember, split ring, DC. Slip ring, when we look at it, there are two of them. They're rings, plural. Here, commutator. Okay? Over here, these are slip rings, because this one slips through. This one should be touching. In fact, one of them should be touching, and the other one will slip through. They just moved in the diagram. This one is at the end. It's touching over there. So please make sure that you're very clear about how these work and the different views of them. It is extremely important. Of course, the last thing that we have is the difference between the hand rules that we use. Now, we've revised them a little bit, but let's just make sure. The motor is going to be the left hand, and remember it's Fleming's left hand rule, and Fleming has an F and an L. That's how we know it's the left hand rule, where the generator is the right hand motor rule. Generator rule. Right hand generator. So that's the FBI rule. So slap your thigh in the FBI, but make sure you can also use the right hand slap rule. Remember, the palm is the unknown. So in the generator, it's going to be the induced current. In the motor, it's the direction of rotation. Guys, I think that helps us just compare the difference between the motor and the generator. So make sure that you've revised this. Recognize the importance of direct current and alternating current, and the association of slip rings with alternating current. Direct current is always the split ring commutator. Don't forget it. Very important. Welcome back, everyone. We're into revising electrodynamics. We've compared the principles that are involved in the electrical machines, and we've compared the features of a motor and a generator. Now let's spend a little bit of time focusing on alternating current, because alternating current is really quite interesting and it has some interesting features. So let's go straight to it as we revise. So the first thing we need to know about alternating current is an induced current. It's formed because you've got a coil moving in a magnetic field. And if that coil changes, it has to change either the magnetic field or the position, the area has to change in some way. So that will cause electromagnetic induction. So because it's an induced current, we recognize that the charges change direction as there's movement. But we also need to recognize that there's an increase and a decrease in the strength of the current. So in a cycle, in a generator, for example, you're going to find the current strength is going to go from 0 to a maximum, back down to 0, then it's going to go negative, maximum, then back up to 0. And that's as the coil rotates in the magnetic field. And so we draw graphs to illustrate that. And the alternating current graph that we're looking at here clearly shows us that there is the 0 point, there is the maximum current, which we call I max, and we recognize here is the I max in the negative region, and it comes back to 0 at those 2 points over there. So as the coil is rotating, it's changing not only the direction of the current, but the size of the current as well. And so we introduced the idea of, well, so what's the effect of this alternating current? Well, we've got to work out a way to say, in what current would it be if it was direct current, in terms of the average power that is delivered to a circuit. If it was direct, what could we replace? So it's an equivalence here. And the way that we've done it is to say, well, let's find the average. Now, you can't just use an ordinary average because the ordinary average would just give you 0. So we use something called a root mean square, which just simply says, you first of all square it, the values, and then you take the square root. And if you do that, you'll find that you get this formula. And the blue line indicates for us the root mean square. Now, I could have put it down at the bottom as well, but I've just taken the positive values here, and this is the formula for calculating root mean square. So it's an important formula, and it is on the data sheet, but please make sure that you refer to it. The important principle here, as we understand this, is that when we look at a machine or we look at a device that is an electrical device, it will have a rating on it. It'll have a power rating, and it will have a current or potential difference rating. Those two will always be the average, the root mean square value, not the maximum. So be aware of that. And as I was saying that, remind you that we've got this idea of voltage. Current and voltage are related. They're related in terms of Ohm's law. R is equal to V over I from Ohm's law. It still applies here. And what you recognize then is that if the current is a maximum, at that same point in time, the potential difference will be a maximum. And if the current is 0 at a particular point in time, then the potential difference will be 0. The difference between these two graphs, though, is this one has gone for more than one cycle. So please be aware of measuring the number of cycles. You will see that this one is the sine graph, and there's 1.5 cycles represented here, whereas in the previous one with the current, I only had 1 cycle represented. But in exactly the same way, we can have V max at the peak over there and over there, whereas we're saying that the VRMS, the average potential difference or voltage, is going to be Vmax divided by root 2. So we are going to use those, and we're going to connect them to the power relationships. And if we recognize the average power is going to be IRMS times VRMS, because power is voltage times current, just in a DC circuit, we can do the same here. The average power will be the average current multiplied by the average RMS. Then we can show that that's equal to half Imax times Vmax, or just the same. We can also use the relationship that has Ohm's law substituted into it. And in this case, we're saying that it's I squared RMS is going to give you the average power times the resistance. The resistance isn't going to change because it's now suddenly an alternating current circuit. It's going to just be exactly what it was before. In this case, average power is equal to V squared RMS divided by R. Now, having looked at those equations, it's important that we get a chance to practice them. And so I want you to make sure you get a piece of paper, a calculator, and get ready to do some questions. Answering previous exam questions is a really good opportunity to test that you can apply your knowledge. Very good way to revise. So take a break now, and we'll see you shortly. Welcome back, everyone. I hope you've got your pen and paper and your calculator, and you're ready to do some revision by looking at some previous exam paper questions. Now, please notice, when you do a question from a previous exam paper, it's not necessarily about getting the right thing, but as you go through it, underline the critical information and help yourself to say, can I remember what's involved here? So let's go through that and let's highlight some ideas. So here's the first question we've got. The story is that the armature of a generator is rotated clockwise at constant speed in a uniform field. Well, that makes absolute sense. If you've got an armature and it's moving at constant speed through a dedicated uniform magnetic field, we know it's going to induce a current. Because it's a closed circuit, the coil is closed, we know that Faraday's law is the thing that says that if you have a changing magnetic flux, it will induce a current. So we know the equation that we're looking for is the induced EMF is going to be equal to minus N delta phi over delta T. The rate of change of magnetic flux is directly proportional to the EMF. And you see what I've done is by highlighting this principle, I've also reminded myself of Faraday's law. And so as I'm looking at what's happening, I'm always saying, what are the links? I'm using the library of information and I'm using the question to trigger the important facts that I need to put together to answer the question. Hasn't asked the question yet, but that was just some initial reading, so I can locate it. So here's the picture now of the generator. Now, what does it actually say? It says, what type of current is produced by this generator? And we're asked to explain your question, explain your answer at least. So it's very important when you get a question that you answer it directly. Don't just launch into an explanation, but make sure that you answer it by saying yes, no, but answer it directly, because there'll be a mark allocated. So what is the question? What type of current? Now remember, there are two types of current. There's direct current, which we say is DC, and there's the alternating current, which is AC. Remember, DC is going to be where current is in the same direction. The charges move in the same direction all the time. Whereas AC, the charges move in opposite directions. They move backwards and forwards, and we recognize that's what's happening. So how are we going to decide what type of current there is? Well, the key thing is to try and focus on what's happening there. This is just the magnetic field. This is a loop, but what's happening at that particular point? between the internal and the external field, or circuit at least. So here, this is the external part, and there's a part in the middle there. So what is that actually telling us? Now, I know that it's a bit blurry, but I still think that you can see something important here. So as I look at it, I can see there's a brush that's making the connection. There's another brush on this side. But if you look carefully at that point there's a split. And I hope you can see that there's only one ring. So this is a split ring commutator. Okay. There are not two rings. There's only one. So it is a split ring commutator. So what do we know? A split ring commutator, is it going to produce or is it going to use DC or AC? Well, split ring commutators are always associated with direct current. So we recognize that this type of current, they've asked us what type of current, so we're going to say the current being produced is direct current. And the reason that you can tell it is that there is a split ring commutator in the circuit or in the generator. Okay? So you need to be looking carefully, collect the evidence, and then give the facts and the reasons for the answer. You don't need to write an essay. All we need to do is to pick out the key information. The key information here is that we know that it's a direct current generator because there's a split ring commutator. But you'll say to me, John, we haven't even looked at a split ring commutator before. We don't know what's going on here. Don't worry, we're going to unpack it as we're looking at it. So please follow me as we go to the next question. So the next part of the question says the position of the armature during a complete revolution changes. These positions are labeled A, B, C, D, and we are then asked an interesting question. It says, at which positions is the current a maximum or a minute? So let's go and have a look. Let's see if we can apply our knowledge. Remember, this is a generator. So we've got to recognize there's motion that is producing an induced current or an induced EMF. Let's have a look at it. So where is it going to be maximum? Where is it going to be minimum? So I've put the south pole over there, the north pole over there. In fact, it should be between each of these. They're just put on top of each other, but you can get the idea. The magnetic field direction is in that direction. The motion is going to be in the clockwise direction. So each of these are rotating. So let's have a look now at what's happening at this position. At position A, we recognize there are field lines that are moving in that direction over there. We recognize that at this point, the coil is also moving in that direction. So in terms of that, what we recognize is that the area associated with the current in that part of the commutator or the whole coil is at 90 degrees. So the coil is sitting over here, the area is over here. Are the field lines cutting through the area? No, because the field lines are running parallel to the area. And they're not cutting through. So remember, it's always the perpendicular area. We're dealing with this idea of phi is equal to B times A times cos theta. We want the perpendicular area. And at this point, over here, the perpendicular area to correct it for it to go through would actually mean that the angle is 90. What do we know about cos 90? 0. So there can be no current in position A. And similarly, there can be no current in position C. So the current here is going to be 0. The current here is going to be 0. The current here is going to be 0. Now, make sure that you understand that at 0, we've got the idea so far, where the current is 0. Let's have a look at what happens as we now rotate the coil into the field. So at this position, what we recognize is we've got a maximum area perpendicular. So the field lines are going to go through there, and it's going to be maximum. So the cos theta here is 0. And that means cos theta is 1. That's going to be a maximum. And similarly, this is going to be a maximum, because cos theta doesn't need to correct. The field lines are going through at 90. So through the area at 90, we don't need to make any correction. So we've got that idea. But do we have any idea about what's actually going to be happening here? Well, it's a very interesting question, because what I need you to understand is if we put some markings onto this terminal, and we say that is AB, and that is CD, so this part is now flipped over. You see it's the brighter white. So this part here will be A, it's closest to us. That part is B. This part will be C. This part will be D. This part now over here at the bottom is A, that's B. This part at the top is C, that part is D. And we can do the same over here, AB. And we can get this part being DC. And I'm not even going to name that one, it's the same as the first one. So if we've got a certain amount of current that's going to go through this coil as it's passing through the field, let's use our right-hand rule, slap rule, to work out, in fact, which direction the current is going. So we'd recognize that if we use north to south as our field lines, we know that in this case, AB is going down, so the current is coming out. So I'm going to say the current is coming out. Let's check it on this side. The field lines are that way. This one is going up, so it's going in on this side. You got it so far? I hope you have, and you're very clear about it. But now watch what happens. At this point, the commutator is connecting in this direction. So there's going to be positive charge at that point, and we're going to have negative at that point, because that's how it's going to circle. It's going to be positive in over here, it's going to be negative, and this is definitely going to be connected in that way. We're going to get a current going through. Now, watch exactly what happens in the next scenario. Over here, the commutator is 0. It's not making any connection. So that would be the other way for us to confirm that that current is 0. But is this current going to be a different current? Is it going to be a negative current? Well, let's have a look and see if it swaps over. You should remember, though, that what the job of a commutator, split ring commutator is. It keeps the current in the same direction. And that's why we call it DC. So let's have a look. Remember what's happening to AB over here. It's going up. And if it's going up, then we'd recognize from our right-hand slap rule, the field lines are that way, that is going up, and what do you notice? The current must be going in. The current is going in there. And what's going over here? This part is going down, so the current is coming out. So if the current was going in over there, that means it must have come in over here, which means it must be positive and that must be negative. So guys, if the reading then is the same, positive, negative, then those maximum must be the same. It's not changing its intensity. It's not going positive, negative, positive, negative. It's going the same way. And that's the whole point of a DC generator. It has a maximum then at which positions? At B and at D. And the minimum is going to be the 0. It's going to be at A, at C, and again at A. So I know that might have been a little bit difficult, but it's not too much for us to be able to unpack. We're given enough information to confirm our ideas as well. Look carefully at the diagrams and unpack the information. And just to make it explicit and very clear, the next question helps us even more. And so this is something that you might not have seen. It tells you to sketch a graph to show how the induced EMF, guys, pick it up. It's not about the current now. It's about the EMF. But remember, the current and the EMF are going to be proportional to each other. So where the one is a maximum, the other is going to be a maximum. Where the one is 0, the other is going to be 0. So we've got a pattern to work with. And it says, sketch the graph of the generator varies, clearly indicate positions A, B, C, D, and A on the graph. And so when we do that, we've got the graph below here. And what is incredibly important, every time you do this sort of graph work, you must make sure that you start your graph in the right place. So remember, we said the current at A was 0, so V here must be 0. We know that V here must be 0 volts, and V here must be 0 volts. So I know I'm going to start in line with that, 0. We know it's going to be a maximum at B. We weren't told what that maximum was, but I'm going to associate that position as being a maximum. So, and this being 0, now, take a note. Because this is a DC generator, it's not going to have a negative voltage. The split ring commutator keeps the direction of the current that is going to the external circuit the same all the time. So if that was the maximum here is going to be positive as well, and the 0 is going to be over there. So if I draw the graph, I'm going to draw a loop like that, where this is going to be referring to Vmax for the DC generator. And we know it's a DC generator because it has a split ring commutator. So get all that information together and you've aced this question. Now, there's one thing that you need to also be able to do. Here's another question where we're given a graph to interpret and we're asked to work in the other direction, to interpret the graph and try and work out exactly what's happening. So the diagram shows the voltage output of a generator. And what do you see? The pattern? It's sinusoidal. It's different to the one that we've just drawn. What are we asked to do? We're asked, the diagram shows the voltage output of the generator. Does this generator have split rings or slip rings? Well, clearly this is AC. It's going backwards and forwards. We also recognize that this is 1.5 rotations. So be very clear about it. What sort of components is it going to have? Well, you must know by now that alternating current over there is always associated with not split ring, don't get that wrong. It doesn't have split rings, it has slip rings. Please make sure that you've got that sorted out. Now, guys, there are a whole lot of other questions that you can practice, but these principles of getting the right association between AC, DC, slip ring, split ring, VRMS, IRMS, power relationships, those are important. So please make sure you do some more practice. I hope you've enjoyed following through the principles of electrodynamics and that you will get top marks for this section. It's something you can really ace because they can't ask too many different questions. If you practice, I know you'll do well. From me, goodbye.